Good morning to everyone. I am Dr. M. Saravanan, working as an assistant professor in Manna Tirumala College, Madurai. Today the topic is application of vulnerability parameters in graphs. So, introduction and motivation, graph theory. So, in school days we gone through the graph, which is a continuous one. Suppose if the elements are discrete one and there is a relation between those things, then we can go for a graph theory. This is a diagrammatic representation of discrete elements and their relations. Generally it is fuzzy graphs. Nowadays the recent topic is fuzzy graphs. The most important property in graph theory is vertex connectivity and edge connectivity. So the vertex connectivity, the least number of vertices to be removed so that the graphs will be disconnected. Similarly, we can define the edge connectivity. The edge connectivity is also defined as the minimum number of edges to be removed so that the graphs will be disconnected. In this, we define the drawbacks and the need for the vulnerability. So the drawback is, suppose if a graph we want to disconnect, we remove some vertices. If you remove some vertices, then the graphs will be or may be disconnected. After then, we cannot say about what about the function of the graph and the remaining set of vertices. So there is no information about the remaining subgraph, and there is no relation between the set and the remaining subgraph. These are the drawbacks of the connectedness in graph. So we need a vulnerability parameter. It defines the number of subgraphs and the purpose, and that is the working function of the graphs and the maximum size of the connected subgraph still working. So there are so many types of vulnerability parameters. One of this is integrity, scattering number, rupture degree. The integrity is defined as the vertex subset, the cardinality of the vertex subset in addition with maximum of connected component. Scattering number is defined as number of component after disconnecting, subtracting the cardinality of the vertex subset. Similarly, the rupture degree is defined as the number of components minus vertex subset minus the maximum connected component. In this presentation, we are concentrating only about the integrity. The integrity is defined by Borefoot in 1987. It defines the stability of a graph. Integrity is defined as the number of vertices to be removed, so that is number of inactive members in a group, and we have to define the maximum size of still working group, that is the largest size of the working group, mathematically defined as the integrity of G is minimum of cardinality of S plus M of G minus S, where S is a subset of P, where M denotes the maximum size of connected component of the graph G after removing the set S. So in this presentation we use the notation G denotes the fuzzy graph, G star is the crisp graph of fuzzy graph, P is the vertex set of G star and V is the edge set of G star. All the remainings are defined for fuzzy graph, and S is the subset of V, and M of G minus is the maximum of the connected component. Now the next topic is, the next heading is application of vulnerability parameters. In 2002, power domination was introduced by Teresa W. Hens and et al. With their partners. They convert a power dominant system monitoring in graphical theoretical terms as vertex, covering and dominating set. S is a power dominating set if every edge and every vertex is monitored by S. Minimum cardinality of power dominating set is power domination number. Assure only one minimum cardinality of a dominating set. If you place a monitoring system at a dominating set, it minimizes the number of PMUs. For example, the power dominating set is a path Pn, and a single PMU is enough to monitor the entire network if the network has a path. Similarly, if you place a PMU in the first node and there is a breakage in the second unit, then we cannot follow the remaining nodes and we cannot take any measures by using PMUs. So, the placement of your PMU is also very important when combining with dominating one. So we define for power dominating. The power dominating set is formally defined as minimum of cardinality of P plus M of G minus P, where P is the minimum power dominating set of G. Consider the graph in the given example. It consists of 6 vertices, namely 1 to 6. If you place a PMU in 2, 3 or 4, the entire network can be covered, that is all the vertices and the edges are observed. So the set singleton set 2, 3, 4 are the 3 power dominating set, and these have the cardinality as 1, therefore the value is 1. That is gamma of P of G is equals to 1. So that is the power dominating set. So we are going for minimal, that is power dominating integrity value. So the power dominating integrity value is if you remove the vertex, that is namely 2 or 3 or 4, the graph should be disconnected 1. After then we have to go for the maximum connected component of that graph. Suppose if I remove 3, so the vertex number 1 is disconnected from the graph, the remaining 3, 4, 5, 6 are linked together. So these 4 vertex plus the removed vertex cardinality is 1, therefore the total number is 5. That is the power dominating set integrity value for the given graph. Now how we can apply the power dominating integrity in power network? First of all, we have to convert the power network as a model, that is a power graph. We have to monitor the power network by using the phase measurement in PMU. Based on Ohm's laws and Kirchhoff's laws, propagation rules are defined. To place a PMU, we need finding the number of PMU to observe the network, and placing the PMU is very important. The power domination problem can be defined theoretically in electrical, that can be converted to a graphical, in graphical terms, such as a bus, that is a vertex in with the PMU, and a line, that is an edge extending from a PMU is observed. Second one, any bus that is incident, that is any vertex that is incident to an observed edge connected to an observed vertex is also observed. Any line, that is any edge joining to observed vertex is also observed. If all the edges incident to an observed vertices are observed, then the remaining one vertices is also observed. Any vertex incident to an observed vertices is also observed. So first thing we have to find, that is we split the problem into 2 parts. First part is we have to find the number of PMUs that needed to observe the vertex. The second part is we have to find where it should be placed. So to finding the PMU needed, find the maximum length subgraph DI with gamma of PDI equals to 1. Delete the edges in DI if all the adjacent edges are DI, and delete that vertex also. So repeat the step until there is no such a one. So the number of edge disjoint components plus number of content vertices minus 1 gives the number of PMU needed. Now we find the number of PMUs needed to observe all the vertex in the power network. The second part is power domination integrity, that is we have to place the PMUs in the given network. So place the PMU in at least one component, that is the maximum largest component, and to place the second PMU in a 2 distance mode. Repeatedly doing, we can observe all the vertices in the power domination, that is power network. We apply this in the IEEE buses, namely 14, 13 and 57. So comparing the result with the topological transformation method in immunity genetic algorithm, and binary particles from optimization method, we get the same result and optimized result 1. So domination parameter optimize, the number of PMUs and the integrity parameter provide the vulnerability to the network. The power dominating integrity provides the optimal integrity of the network. The optimal solution obtained is compared with some efficient method and proved better than the normal condition. Thank you for your patience. Thank you.